Hi students, today I am going to deal with the topic light sources which are used in spectral analysis. We are going to deal with the light sources which are used in spectral analysis. The learning objectives. Upon completion of this presentation, you will be able to understand the sources of light that are used in spectral analysis, the property of the different light sources, the types of radiation sources which you are going to use in the visible region, UV region and IR region. Upon completion of this presentation, you will be able to understand the different sources of light, the properties of the light sources and the types of radiation sources which are used in the visible region, ultraviolet region and infrared region. Once again, we would like to define what is spectroscopy. Spectroscopy is the branch of science dealing with the interaction of matter with the electromagnetic radiation. Spectroscopy is the branch of science which deals with interaction of matter with the electromagnetic spectrum. It is an analytical technique which helps to determine the structure of molecules in a sample. It is an analytical technique which helps to determine the structure of molecules in a sample. Types of spectroscopy. Spectroscopy is of two types: atomic spectroscopy and molecular spectroscopy. Atomic spectroscopy deals with the interaction of electromagnetic radiation with atoms. Molecular spectroscopy deals with interaction of electromagnetic radiation with molecules. So once again, I would like to repeat that spectroscopy is a branch of science which deals with interaction of matter with electromagnetic radiation. It is a technique which helps to determine the structure of molecules in a sample. And spectroscopy is classified into two types. First one is the atomic spectroscopy and second one is the molecular spectroscopy. The atomic spectroscopy deals with interaction of electromagnetic radiation with atoms, whereas molecular spectroscopy deals with interaction of electromagnetic radiation with molecules. When we see the electromagnetic radiation, the electromagnetic spectrum, which ranges from gamma rays to radio waves, the shortest wavelength to the longest wavelength, we have the different regions here. The energy of the electromagnetic spectrum, we have the gamma rays, its wavelength is 10 power minus 10 nanometers to 10 power minus 3 nanometers. Then we have the X-rays are of they are also shortest wavelength, having shortest wavelength which forms the electromagnetic spectrum. They are from 15 nanometers to 10 power minus 2 nanometers. Then we have far ultraviolet which ranges from 200 nanometers to 15 nanometers. Then ultraviolet which ranges from 400 to 200 nanometers. And visible region which ranges from 400 to 800 nanometers. And then we have near infrared which ranges from 0.8 micrometers to 2.5 micrometers. And we have the infrared region which ranges from 2.5 micrometers to 15 micrometers. And we have the far infrared which ranges from 15 micrometers to 200 micrometers. And the microwaves which are from 10 power minus 2 centimeters to 30 centimeters. And radio waves which range from 30 centimeters to 2 into 10 power 6 centimeters. So this is the energy, the electromagnetic spectrum ranges between these wavelengths. The wavelength range is observed in the figure shown. Now coming to the spectroscopic analysis, mostly we are using the UV, visible and ultraviolet regions of the electromagnetic spectrum for spectral analysis. For the spectroscopic analysis, we are mainly using the ultraviolet region, the visible region and the infrared region of the spectroscope. We are using the ultraviolet region, the visible region and the infrared region for the spectroscopic analysis. So coming to the first one, the ultraviolet region. The ultraviolet region is a form of UV is a form of electromagnetic radiation with wavelengths from 10 nanometers with a corresponding frequency of approximately 30 picohertz to 400 nanometers. It's 750 THz, shorter than that of the visible light but longer than the X-rays. They are shorter than the visible light but longer than the X-rays. Then comes the visible region. The visible spectrum is the portion of the electromagnetic spectrum that is visible to the human eye. Electromagnetic radiation in this range of wavelength is called visible light or simply light. A typical human eye will be able to respond to wavelengths from about 380 nanometers to 740 nanometers. This is the range of the visible spectrum. Then the infrared region. The infrared region, sometimes called as infrared light, is the electromagnetic radiation with wavelengths longer than those of the visible light. It is therefore generally invisible to the human eye. Its wavelength is longer than that of the visible light. So it is not visible to the human eye. Although IR at wavelengths up to 1050 nanometers from specially pulsed lasers can be seen by humans under certain conditions, IR wavelengths extend from nominal red edge of the visible spectrum at 700 nanometers to 1 millimeter. This is the infrared region. So for spectroscopic analysis, we are going to use the ultraviolet, the visible and the infrared regions. So different light sources are used. As you know, the first one in the basic block diagram of analytical instrumentation, we have seen the first block. The first block is a chemical information source where you are going to give a stimulus to the sample. The stimulus is given from the source of light. So the radiation source plays a very vital role in analytical instrumentation. So light is an electromagnetic radiation. Hence, emission of light from any source results from the acceleration of the electric charges. These electric charges involved in the emission of visible and ultraviolet light and are the negative electrons in the outer part of the atom. By assuming the orbital or vibratory motions of these electrons cause radiations, many of the characteristics of different light sources which can be explained later. So light is an electromagnetic radiation. Hence, how this emission of light takes place from any source? It results due to acceleration of the electric charges. What are these electric charges? They are evolved in the emission of visible and ultraviolet lights, they are the negative electrons in the outer part of the atom. By assuming the orbital or vibratory motions of these electrons causes radiations and whose characteristics differ for different sources of light. Properties of the sources of radiation. The next topic we are going to deal with is the properties of sources of radiation. The properties of a radiant source. What are the basic properties? A source must generate a beam with sufficient radiant power for easy detection and measurement. The source must generate a beam with sufficient radiant power. The power generated by the radiant source must be sufficient enough for easy detection and measurement. That is the first fundamental property of a radiant source. Then the second one is its output power should be stable for reasonable period. Its output power should be stable for reasonable period. The third one is the intensity should not fluctuate. The intensity of the radiant source, it should not fluctuate. It should not vary. It must remain constant over long and short time intervals. These are the three common properties of any radiant source. The properties of a radiant source are: a source must generate a beam with sufficient radiant power for easy detection and measurement. For easy detection and measurement, you need the source to generate a beam with sufficient radiant power. And also the second one is its output power should be stable for reasonable periods. Its output power should not fluctuate. It should not vary. It should be stable for reasonable period of time. Then the third one is the intensity should not fluctuate over long and short time intervals. You should remember that the output power of the radiant source should not be unstable, but it should be stable for reasonable period of time, and also its intensity should not fluctuate over long and short time intervals. Coming to the next is the classification of radiant sources. What are the types of radiation sources? There are two types of radiation sources. The first one is continuum sources and line sources. What is continuum sources? Continuum sources of radiation which emit radiation over broad wavelength range. They emit radiation over a broad wavelength range, and the intensity of the radiation changes slowly as a function of wavelength. Okay, continuum sources are sources of radiation which emit the radiation over broad wavelength range, and the intensity of the radiation changes very slowly as a function of wavelength. The second one is the line sources. Light sources that are capable of primarily emitting radiation with discrete well-defined frequencies are called line sources, which are widely used in spectroscopy. We have two types of sources, radiation sources. The first one is the continuous sources and the second one is the radiant line sources. The continuum sources are sources of radiation which emits radiation over a broad wavelength range, and the intensity of the radiation changes slowly as a function of wavelength. The second one is the line sources. Light sources that are capable of primarily emitting radiation with discrete well-defined frequencies are also widely used in spectroscopy, and they are termed to be line sources. Continuum sources. Continuum sources emit radiation over a wide range of wavelengths. They emit radiation over a wide range of wavelengths. The intensity of the emission varies slowly as a function of wavelength. These are the characteristics of continuum sources. They emit radiation over a wide range of wavelength. Continuum sources emit radiation over a wide range of wavelengths. The intensity of the emission varies slowly as a function of wavelength. and they are used for most molecular absorptions and fluorescence spectrometric instruments. These continuum sources are used for molecular absorption and fluorescence spectrometric instruments. Fluorescence spectrometric instruments. The examples of continuum sources, these are the various examples of continuum sources. Continuum sources are those radiant sources whose, what are the features of continuum sources? There are those sources of radiation which emit that radiation over broad wavelength ranges, and the intensity of the radiation changes very slowly as a function of wavelength. The examples of continuum sources are tungsten filament lamp, which is used in the visible radiation. Then we have deuterium lamps, which are used for UV radiation, high pressure mercury lamps, ultraviolet radiation, xenon arc lamps, ultraviolet and visible region, heated solid ceramics, they are used for IR region, that is the infrared region, and heated wires, they are for infrared region. So some of the examples of continuum sources are, tungsten filament lamps, visible radiation, deuterium lamp, UV radiation, high pressure mercury lamp, UV radiation, xenon arc lamp, UV and visible region, heated solid ceramics, IR region, heated wires, IR region. So these are the examples of continuum sources. So we'll take the first example, that is tungsten filament visible radiation. It is used, tungsten filament lamp, which is used in visible radiation. It glows in this tungsten filament lamp glows at a temperature of 300 degrees centigrade. Tungsten filament lamp. 300 degree Kelvin. Produces radiation at a wavelength from 320 to 2500 nanometers. 2500 nanometers. And they produce the radiation between 320 to 2500 nanometers. Hence, they are used in visible and near infrared region. These tungsten lamps are also called as quartz halogen lamps. The tungsten lamps are also called as quartz halogen lamps, which contains a very small amount of iodine within the quartz envelope. You have seen that bulb there, glass bulb in the picture. The glass bulb contains the tungsten filament and it is filled with quartz or halogen lamps. They are also called as quartz or halogen lamps, which contain a small amount of iodine within the quartz envelope that houses the filament. Quartz allows the filament to be operated at a temperature of 3500 degree Kelvin, which leads to higher intensity and extends the range of the lamp well into the UV region. The lifespan of this tungsten halogen lamp is more than double that of the ordinary tungsten lamp. Instead of using only the tungsten lamp, we are using tungsten halogen lamps. Why we are using the tungsten halogen lamps is to increase the lifespan of this lifetime of the lamp, because the life of the tungsten halogen lamp is limited by sublimation of the tungsten from the filament. Okay, what actually happens in tungsten halogen lamps are, they are nothing but special class which has the halogen gases filled inside the bulb. The envelope is fabricated of quartz to tolerate the very high temperatures of about 3500 degree Kelvin. The iodine combines chemically at the bulb wall with sublimed tungsten. This tungsten begins to sublime. The resulting Wi2, that is tungsten iodine gas, migrates back to the hot filament where it decomposes and tungsten is redeposited. That is why this has become very famous. Which one? The tungsten halogen lamps have become famous when compared to tungsten filament lamps. Simply tungsten filament lamps have the tungsten wire and inert gas filled inside the bulb. In addition to that, if you are using the halogen gases like iodine, what happens? This iodine, it combines with the tungsten, which is formed as a sublimate on the walls of the bulb, and at such high temperatures they produce tungsten iodine gas, which deposits which decomposes. This gas migrates to the hot filament, it decomposes and tungsten is redeposited there. So this is the advantage of tungsten filament halogen lamps. So they produce electromagnetic radiation in the wavelength of 320 to 2500 nanometers. For this reason, it is used in the visible and IR region, because most of the visible region is covered in this radiation. So this is the lamp. Tungsten filament lamp is used for visible region and near infrared region. Then comes the continuum source. One of the next example of a continuum source is mercury and xenon arc lamps. Mercury and xenon arc lamps. In the mercury and xenon arc lamps, electric discharge lamps, these are called electric discharge lamps. They produce radiation. Electric discharge lamps, they produce radiation at wavelengths from 200 to 800 nanometers. 200 to 800 nanometers. They produce between 200 to 800 nanometers. And hence these mercury and xenon arc lamps, where the discharge is produced inside the bulb, inside the tube. You have an anode and a cathode in an envelope. The anode and cathode is placed inside inside an envelope, where you have the anode is heated and you are using the mercury and xenon arc lamps here. In this lamp we have the electric discharge lamps. They produce radiation at wavelengths from 200 to 800 nanometers. 200 to 800 nanometers. 200 to 800 nanometers. Then comes your next important continuum source is deuterium arc lamps. Deuterium arc lamps. They are sometimes also called as hydrogen deuterium arc lamps. These lamps, where deuterium molecules are electrically dissociated. When deuterium molecules are electrically dissociated, they are called hydrogen or deuterium discharge lamps or arc lamps, they are also called. They produce radiation at a wavelength of 200 to 400 nanometers. That is why they are mostly used in ultraviolet region. These deuterium arc lamps are used in the ultraviolet region. Hydrogen or deuterium, they are also called as discharge lamps. Hydrogen or deuterium arc lamps or discharge lamps are used in the UV region and are operated at a very low temperature. They are operated at a very low temperature. They are operated at a very low temperature, very low pressure, They are operated at a very low pressure of 0.2 to 5 torrs. And low voltage approximately 40 volts DC. They are operated at low voltage of 40 volts DC condition. Heated cathode provides the essential function of maintaining the discharge. Inside that you have the cathode which maintains the discharge. The discharge has negative temperature versus resistance characteristics. And the vital feature of these lamps is a mechanical aperture between the cathode and the anode, which constricts the discharge to a narrow path. There is a small aperture inside, because of which you are going to restrict or constrict the discharge to a narrow path. Normally, the anode is placed close to the aperture, which creates an intensity radiation falling on intensity radiant ball of light about 0.6 to 1.5 mm in diameter on the cathode side of the opening. On the cathode side of the opening. So the use of deuterium in place of hydrogen slightly increases. When you are using deuterium, sometimes hydrogen arc lamps they are also called as hydrogen arc lamps. Instead of hydrogen, you are using deuterium. The size of the light ball increases, and also the brightness changes from 3 to 5 times. The brightness changes from 3 to 5 times. It is well used in the UV region because it produces radiation at wavelengths of 200 to 400 nanometers. 200 to 400 nanometers. Then coming to the next one is your line sources. Line sources. So what are line sources? When we went to the first classification of different type of sources, we have seen that the sources are classified into two types: continuous sources and line sources. Line sources are those sources which are capable of emitting a radiation with discrete, well-defined frequencies. So emit only few discrete, well-defined frequencies or wavelengths. So they emit only a few discrete wavelengths of light. Intensity is a function of wavelength here also, and it is used for molecular and atomic and Raman spectroscopies. Used for molecular, atomic and Raman spectroscopy. Line sources. Line sources emit radiation with discrete, well-defined frequencies. With discrete, well-defined frequencies. They emit only a few discrete wavelengths of light. Intensity is a function of wavelength here, and use it for molecular and atomic and Raman spectroscopy. The examples of line sources are hollow cathode lamp. Hollow cathode lamp. It is used in UV and visible regions. Hollow cathode lamp. Then the second one is electrodeless discharge lamp. Electrodeless discharge lamp. The third one is sodium vapor lamp. Sodium vapor lamp, which is used in the UV and visible region. Then the mercury vapor lamp, UV and visible region. The last are the lasers. The last are the lasers. So examples of line sources are hollow cathode lamp, UV or visible region, electrodeless discharge lamps, UV and visible regions, sodium vapor lamps, UV and visible regions, mercury vapor lamps, UV and visible regions, and lasers, which are used in UV, visible and IR regions, all the three. So these are the examples of light sources which are used in examples of line sources. Examples of line sources. We have the electric discharge, electrodeless discharge lamps. Then we have the lasers. We have the halo cathode lamps. Halo cathode lamps. These are the figures for different types of some of the types of line sources. The first one we are going to deal with is electrodeless lamp, discharge lamp, or UV, which is used in UV and visible region. An electrodeless arc lamp comprises an outer jacket. It consists of an outer jacket hermetically sealing and thermally protecting an arc tube inside which an upwardly convex bottom center section. So you have a electrodeless arc lamp. It comprises an outer jacket hermetically sealing and thermally protecting an arc tube. There is a tube inside which is protected, and that tube is protected, protecting an arc tube which is inside, which has an upwardly convex bottom center section. The absence of chemically reactive electrode material makes it possible to use metal halides. The absence of chemically reactive electrodes material makes it possible to use metal halides other than iodides. The tube contains chlorides, bromides, or mixture thereof of scandium and sodium in a nearly equimolar relationship, in addition to mercury and inert gas. Good color balance can be obtained at reduced reservoir temperature and with less power loss. Reduction in vault temperature makes it possible to attain longer life. Then coming to the next is your next type of line sources, that is hollow cathode lamp, which is used in the UV and visible region. A hollow cathode lamp, HCl, it is also called as HCl short form, is a type of cold cathode lamp which is used in physics and chemistry as a spectral line source. It is used in spectral analysis and as a frequency tuner for light sources such as lasers. This HCl is nothing but hollow cathode lamp. It is commonly used as a frequency tuner for light sources such as lasers. Hollow cathode lamp, UV and visible region. And HCl takes advantage of the hollow cathode effect, which causes conduction at a lower voltage and with more current than a cold cathode lamp that does not have a hollow cathode. So you are using the hollow cathode effect, which causes conduction at lower voltages than a cold cathode. An HCl usually consists of a glass tube containing cathode and an anode, and a buffer gas, usually a noble gas, is used inside the discharge. As they are all lamps or discharge tubes, we have an anode and a cathode, and here the cathode and anode are there, and you are having a buffer gas inside, which is usually made up of a noble gas. A large voltage across the anode and cathode will cause the buffer gas to ionize, creating a plasma. The buffer gas ions will then be accelerated into the cathode. Sputtering of the atoms from the cathode. Both the buffer gas and the sputtered cathode atoms will in turn be excited by collision with other atoms and particles in the plasma. As these excited atoms decay to lower states, they will emit photons, which can then be detected, and a spectrum can be determined. So what is happening in a hollow cathode lamp? HCl usually consists of a glass tube containing a cathode. It consists of a glass tube which contains a cathode and an anode. You have a buffer gas, also usually made up of noble gas. So a large voltage across the anode and cathode will cause the buffer gas to ionize. The gas is placed inside the envelope. So what happens when a large voltage is applied across the anode and the cathode? The buffer gas begins to ionize, creating a plasma. The buffer gas ions will then be accelerated into the cathode and sputtering of the atoms of the cathode takes place. Sputtering of atoms from the cathode takes place. So both the buffer gas and these sputtered cathode atoms will in turn be excited by collision with other atoms or particles in the plasma. Both the buffer gas and the sputtered cathode atoms will in turn be excited by collisions with other atom particles in the plasma. As these excited atoms decay to these excited atoms, they cannot stay in that state for a longer time because they are unstable. They try to come back to their stable state. During this process of coming back to the stable state, these excited atoms decay to the lower state and they will emit photons, which then photons are nothing but packets of energy or light, which can then be detected and a spectrum can be determined. And this radiation which is being emitted is usually in the UV and the visible region. The radiation emitted is usually in the UV and visible region. It is in the UV and visible region. So coming to the next, till now we have seen the sources of radiation, the classification of two types of sources of radiation. That is, the first one is the continuum sources and the second one is the line sources. In the continuum sources, we have seen three basic types of continuum sources. That is, we have seen tungsten filament lamps. We have seen tungsten filament lamps. We have seen the deuterium lamps, mercury xenon arc lamps and deuterium arc lamps. Then coming to the next one are the different types of line sources. What are the line sources? Line sources we have already discussed earlier. Line sources emit only few discrete wavelengths of light. They emit only few discrete wavelengths of light, and the intensity is a function of wavelength. They are used in molecular and atomic and Raman spectroscopy. The first one is your, in the line sources we have seen so commonly used line sources are the commonly used. So we have the line sources here. The most commonly used line sources. So we have the line sources, that is another example of the line sources are commonly used line sources are. What are the commonly used line sources? We have the figure. In the previous figure we have the line sources. The line sources emit only a few discrete wavelengths of light. Intensity of is a function of wavelength. Used for molecular and atomic and Raman spectroscopy. Then we have the line sources are classified in, most commonly used is electrodeless discharge lamps and lasers and hollow cathode. So the commonly used light sources are, which are used in UV and visible and infrared regions are tungsten filament lamps, which are in the visible radiation, deuterium lamps, which are used in UV radiation, xenon arc lamps, UV and visible region, hollow cathode lamps, and electrodeless discharge lamps and lasers. So we have studied about hollow cathode lamps. We have studied about the three types. We have studied about the three types of line sources. That is the hollow cathode lamps we have studied. Then we have studied about the first type is the Electrodeless discharge lamps we have seen. We have seen the electrodeless discharge lamps. We have seen the line source hollow cathode lamps. We have to study the laser lamps. In the laser lamps, lasers are nothing but light amplification by stimulated emission of radiation. Light amplification by stimulated emission of radiation. These laser light sources are used in all the three regions: UV, visible, infrared regions. Laser is light amplification by stimulated emission of radiation. It produces specific spectral lines used when high intensity line source is required. It is used when high intensity line source is required. Produce specific spectral lines. They produce specific spectral lines. They are used when high intensity line sources are required. When high intensity line sources are required, these laser line sources are used in all the three regions: UV, visible and IR regions. Okay, they can be used for UV, visible and FTIR, that is Fourier transform infrared region. Fourier transform infrared region. And one more thing I would like to tell you here, among the different line sources, what are the different line sources? We have hollow cathode lamps, we have electrodeless discharge lamps, sodium vapor lamps, mercury vapor lamps, laser, ultraviolet and visible lamps. Among all these things, why laser is the best or most commonly used these days? They are incandescent lamps. Why they are better? They are incandescent lamps. They have many wavelengths. These laser lights have many wavelengths, multi-directional. These are the features why we are using lasers. They are incoherent. Incandescent lamps have many wavelengths, whereas lasers are monochromatic. Incandescent lamps are multi-directional, whereas lasers are directional. Incandescent lamps are incoherent, whereas laser lights are coherent. So this is the difference between lasers and incandescent lamps. In incandescent lamps like the tungsten filament lamps, all these lamps, they are used in many wavelengths. Okay, but here they are specific. As I told you, laser lamps are produce specific spectral lines with very high intensity. Okay, high intensity line source, if you need of specific spectral line, we go for lasers because they are monochromatic and they are not multi-directional, but they are directional. They are not incoherent, they are coherent. We have different types of lasers like solid state lasers, gas lasers, we have tunable lasers, we have semiconductor lasers. These are the different types of lasers. The first among them is the solid state laser, where we are having the ruby laser. Ruby laser is one of the first laser. Ruby is a synthetic material, synthetic aluminum oxide with chromium oxide added to it. Okay. So pumping is by the light from the xenon flash lamp. Then we have the other solid state lasers like neodymium YAG lasers. Then we have gas lasers are also there. Then we have tunable lasers are there, gas lasers, semiconductor lasers are there, like the LEDs, which almost LED, light emitting diodes, they emit almost anywhere in the spectrum from UV to IR. The infrared, the LEDs, they emit radiation from UV to IR. That is why laser light sources are predominant these days, and efficiency is much higher than other systems. Okay, so LEDs are there. So these are the areas where laser light amplification stimulated emission of radiation. Light amplification, stimulated emission of radiation, where the radiation produced is of specific spectral lines. These lasers produce radiation of specific spectral lines, and they are used when high intensity line sources are required. When high intensity line source is required, we go for lasers. They can be used in all the three regions, ultraviolet, visible and IR regions. They are better than incandescent lamps. Why? Because they are monochromatic in nature, they are directional, and they are coherent. These are the three factors which make lasers more demanding when compared to other types of incandescent lamps. And when we come to the case of the classification of lasers, solid state lasers, gas lasers, tunable lasers and semiconductor lasers, in the semiconductor lasers, LEDs are most commonly used. They produce radiation in the LEDs produce radiation in UV to infrared, from UV to infrared. So they cover the entire range of the range which is needed for spectroscopic analysis. So lasers are most commonly or mostly used. Lasers are mostly used as light sources for emission of for spectroscopic analysis. Coming to the summary, I would like to summarize what we have learned today. We have learnt about the sources of light. We have learnt about the sources of light. Once again, I would like to recollect what we have learned today. We have learnt about the sources of light. What are the sources of light? There are three basic sources. Why the light source is needed? Light source is nothing but the fundamental chemical information source. The stimulus that is given to the, it is the stimulus that must be given to the sample so that the sample interacts with the radiation produced from the light source and it produces some information. Some analysis must be done. So the light source is very, very important. So light is an electromagnetic radiation, and hence emission of light from any source results from the acceleration of the electric charges. And these electric charges involved in the emission of visible and ultraviolet light. They are involved in the emission of visible and ultraviolet light. So light sources are very, very important in spectral analysis. So we have studied about the properties of light sources. What are the basic properties of light sources? Light source must generate a beam of light with sufficient radiant energy, radiant power for easy detection and measurement. The light source must be able to generate a beam with sufficient radiant power for easy detection and measurement. Then its output power must be stable for a reasonable period of time. Then its intensity should not fluctuate over long or short time intervals. These are the basic requirements of a light source. Then coming to the types of radiation sources, we have studied about two types, the continuum sources and the line sources. In the continuum sources, the source of radiation emits the radiation over broad wavelength range, and the intensity of the radiation changes slowly as a function of wavelength. Then we have the line sources. The line sources are capable of primarily emitting radiation with discrete well-defined frequencies, and these are widely used in spectroscopy, line sources. Okay. Then commonly used light sources which are commonly used, the continuum sources are of two types. There are several examples of continuum sources which we have discussed, that is tungsten filament lamps, deuterium lamps, high pressure mercury lamps, xenon arc lamps and heated solid ceramic lamps. Among them, the tungsten filament lamps are used in the visible region. They glow at a temperature of 3000 degree Kelvin and produce a wavelength from 320 to 2500 nanometers, and hence they are widely used in visible and infrared, near infrared region. Then you have the mercury and xenon arc lamps. The mercury and xenon arc lamps, they produce radiation at 200 to 800 nanometers. 200 to 800 nanometers. Therefore, they are well suited for UV and visible region. Then we have deuterium arc lamps or hydrogen arc lamps. They produce radiation between 200 to 400 nanometers, and hence they are well used for UV region. They are well used for UV region. Then we coming to the line sources. Line sources are the light sources which emit only a few discrete wavelengths of light. They emit only a few discrete wavelengths of light, and their intensity is a function of wavelength. So there are several examples of line sources: hollow cathode lamp, electrodeless discharge lamps, sodium vapor lamps, mercury vapor lamps, and lasers. Some of the examples of line sources are commonly used: electrodeless discharge lamps or hollow cathode lamps, and lasers. Electrodeless discharge lamps, they are lamps which comprise an outer jacket, and the absence of chemically reactive electrode material makes it possible to use metal halides other than iodides. Okay. Hollow cathode lamp is a type of cold cathode lamp used in spectral analysis, and it is also used as a frequency tuner for light sources such as lasers. Okay. Then we have studied about lasers. Lasers are nothing but light amplification by stimulated emission of radiation. They produce specific spectral lines used when high intensity line source is required, and they can be used in all the three regions, that is the visible region, ultraviolet region, and the infrared region. Ultraviolet region and the infrared region. And one of the the advantage of using lasers when compared to the incandescent lamps are: lasers are monochromatic in nature, they are directional, and they are coherent. These three features make lasers most commonly used these days. Lasers are divided into four types: solid state lasers, gas lasers, tunable lasers, and semiconductor lasers. And among them, we have also the coming to the classification of semiconductor lasers. We have the LEDs, light emitting diodes. They emit almost everywhere in the spectrum, right from the UV to the infrared. So they are commonly used in all the three regions, the LEDs, and their efficiency is much higher than the other optical pumping systems, and they are used in integrated optics. So these are the advantages of using lasers when compared to all other light sources. So with this, we will end our presentation today.